All right, here's an example set on exponential growth. So we have a table that shows you the transistors in a chip. So it starts off in 1965 with 60 transistors. Then a year goes by and notice that number doubles to 120. The next year it goes to 240, so it's doubling. So we say that this is an exponential growth model because as the x's increase, so do the y values. So we can write this as an exponential function. So here's what an exponential function looks like. It has a base of b, which has to be greater than 0 and cannot be 1. And then it has an exponent, a power there, and that's what you input in for x. Then if your base is greater than 1, it's going to grow over time. If the base is a fraction, it's going to decrease over time. So as the x's increase, the y's will decrease. The last thing on this slide to note is when you have a negative exponent, what you can do is you can flip that base and you would now have a positive x squared. Example 1 says graph the parent function of f of x equals 2 to the x. So what we do is we evaluate the exponent. So this is what the table looks like. These are our domain values and these are our range values. So how do we get this ordered pair right here? So I'm going to show you below. So what we do is we input the domain, the x, into the exponent. So then 2 times 2 is 4. So that ordered pair then, when we graph it, is going to be over 2 up 4, which is right here, over 2, 4. If we wanted to graph a fraction, or input a fraction, it's not in this table here, we'd want to use our calculator. So you would input that into your graphing calculator, your scientific calculator, and you get approximately 1.4. So when we go over 1/2, we go up 1.4. So that'd be about there. And then we would graph the rest of these ordered pairs, and we would get this exponential function in the red. Now we do have an asymptote. It's a little hard to tell here. It's on this green line here. We say it's a horizontal asymptote at y equals 0. The graph is approaching the green line but does not touch it. So our domain for this function, what can we plug in for x? We can plug in all real numbers, so negative infinity to infinity. And then what do we get out? Our range of values is everything from this green line right here and higher. So y is greater than 0. Okay, now we're going to go ahead and graph one by hand. So we have a function f of x equals 10, and then we have a base of 3/4. So that's our base, which is a fraction. So is that going to be growing or decaying? In this case, it's going to be decaying because it's a number greater than 0 but less than 1. And then what we do is we create a table and we would input domain values in for the exponent. So I'm going to start with -1. And then we want to just use our calculator and input that in. We get approximately 13. . So then we go left 1, up 13. Then we would input 0 into the exponent. And when we're done, we get 10. So we graph the ordered pair over 0, up 10. Then we input 1 into the exponent. And we get 7.5. So we graph the ordered pair right 1, up 7.5. Then we input 2 into the exponent. And we get approximately 5.6. So we go right 2 up 5.5. Last one, we'd input 3 into the exponent. We'd use our calculator to simplify. We get approximately 4.2. So we graph that right 3 up 4.2. And then we would connect our points. Then what we're going to have is a horizontal asymptote, just like its parent, at y equals 0. All right, for the domain, you can substitute any number into the function, so it's all real numbers. The range of values is everything above that red horizontal asymptote, so y is greater than 0. All right, here's another example. So this time our base is 2, and that number is greater than 1, so it's going to grow over time. Then we would input our numbers into the exponent. We get 2. So then we're left 1 up 2, and I'm just going to wait on graphing these ordered pairs until after I'm done doing my evaluating. Then we'd input 0. Into the function, and we get 4. Then we input 1 into the function, and we get 8. We input 2 into the function, we get 16. So notice what's happening, those numbers are doubling. Input 3 into the function, all right, now we graph the ordered pairs. And we notice that this graph is increasing over time. It has the same horizontal asymptote at y equals 0. The domain is all real numbers. The range is everything greater than that horizontal asymptote. Notice where our y-intercept now is over 0, up 4. Where when we had our parent here, we had the same base, but our y-intercept was at 0, 1. So what did that 4 do to the problem? It just moved that y-intercept up to 4 units instead of at 0, 1. There are some check for understanding problems if you'd like to do before we come to class tomorrow.